Welcome to our Quantum Deep Dive. Today, we're doing something really unique. We're diving deep into artificial intelligence, specifically natural language processing, NLP. But we're not just looking at what it is today. We're exploring how quantum computing, that really mind-bending field, might totally reshape its future. And our guide for this is a fantastic, really insightful essay by Jorgo Schneepad. Our mission here is to pull out the absolute key insights from his work to give you a clearer picture of, where language processing could be heading. Okay, so NLP. We all use it constantly, right? Often without even realizing. Think about asking Siri something or using Google Translate. NLP is working behind the scenes there. For those of us who follow this space, we know it's come such a long way. It's this mix of computer linguistics, AI, machine learning. But even with all that progress, what are the big roadblocks it's still hitting?
It really is fascinating, the journey NLP has taken. The early systems were very rigid, purely rule-based, like Joseph Weizenbaum's ELIZA back in the 60s. Groundbreaking then, sure, but easily confused by just how variable language is. Then we saw a big shift, moving towards statistical models, classic machine learning, things like naive Bayes, support vector machines. They got much better by learning from huge amounts of text data. But the real revolution, what we see now, is deep learning, especially these transformer architectures like BERT and GPT. And the key thing there, the sort of secret sauce, is the attention mechanism. It's basically how these models figure out which words in a sentence are most important for understanding the context. It lets them grasp meaning much more accurately.
Right. But even with these really powerful transformers, we're still seeing limitations, aren't we? It feels like there's some fundamental ceilings. What are those big hurdles?
Absolutely. It's not just about needing, more data or faster chips, although that's part of it. Classical NLP seems to be hitting some real bottlenecks. One huge one is just the sheer computational power needed. GPT-3, for instance, trained on, 570 gigabytes of text?
Wow.
Yeah. That needs specialized hardware, massive amounts of energy. Another big challenge is understanding long-range context.
Yeah.
Even with attention, transformers can kind of lose the thread over very long pieces of text. And then there's just the ambiguity built into language itself. Like that classic example, I saw him with the binoculars.
Ah, yeah. Who has the binoculars?
Exactly. Humans get that nuance instantly. Algorithms, they really struggle with that kind of ambiguity. It's a constant challenge.
That's a really good point. It makes you wonder, are people looking at completely different ways to do this?
Okay.
Besides just bigger neural networks, is there another approach?
Oh, definitely. While neural nets are dominant, there's also symbolic AI that uses logical rules, knowledge graphs. It's often more explainable. You can usually see why it made a decision. But the trade-off is often flexibility. It struggles more with the fluid, messy nature of real language compared to neural nets. Different philosophy, really.
Okay, so with those challenges for classical NLP, it sounds like we need something radically different. And that, I guess, brings us squarely to quantum computing. Mm-hmm. For anyone less familiar, how is this such a completely different way of thinking compared to the usual zeros and ones?
Well, the absolute core difference is the basic unit of information. Classical computers use bits 0 or 1. That's it. Quantum computers use qubits. And a qubit, it can be 0, it can be 1, or crucially, it can be a combination of both at the same time. That's superposition.
Okay.
And it's not just a neat trick. It means a quantum computer can explore loads of possibilities simultaneously. Then you've got entanglement. This is where qubits get linked. The state of one instantly affects the other, no matter how far apart they are. It's weird, but powerful for processing information.
Weird is right.
Yeah. So you combine superposition and entanglement, and you get what's called quantum parallelism. The ability to process just an exponential number of states all at once, that makes them potentially amazing for certain kinds of really complex problems that would just choke a classical computer.
That sounds incredibly powerful. Are there specific quantum algorithms that really show off this potential, this speed up?
Yeah. Two really famous examples come to mind. First is Grover's algorithm. It gives you a quadratic speedup for searching unsorted data. Imagine looking for a number in a huge random phone book. Classically, you might have to check every entry. Grover's algorithm can find it much, much faster. A really significant boost for searching large data sets.
Okay, that makes sense for search.
Then there's Shor's algorithm. This is the big one everyone talks about with encryption. It's incredibly efficient at factoring large numbers. And factoring large numbers is, the mathematical basis for a lot of our current encryption, like RSA that protects online banking and stuff.
Right, so Shor's algorithm could potentially break that.
Theoretically, yes. A large enough, stable quantum computer running Shor's could break current RSA encryption quite easily. It really highlights the disruptive power we're talking about.
Wow. Okay. That difference between classical and quantum is huge.
Yeah.
So bringing it back to NLP, given these quantum abilities, how does that actually start to help a field like NLP, which has always been about classical computing? Why should NLP folks care?
Well, it really comes back to those computational hurdles we talked about earlier. These big NLP models, transformers, they have billions of parameters. Training them, running them, it takes huge amounts of time, energy, resources. The complexity often scales really badly.
Right, like ON2 sometimes.
Exactly. So that's where quantum could potentially step in. It's about this idea of quantum supremacy or quantum advantage, where a quantum computer can do specific calculations exponentially faster. Grover's algorithm, for instance, could dramatically speed up core NLP tasks. Think semantic search, classifying text, finding clusters of similar documents, finding patterns faster.
So it's not just doing the same things faster. Maybe it enables new kinds of processing too.
That's the hope. Yeah, beyond just speed-ups, we're starting to see things like quantum neural networks, QNNs. They try to merge neural network ideas with quantum mechanics, and maybe even more intriguingly, things like quantum Boltzmann machines, QBMs. Imagine a language model that doesn't just process words, but uses quantum effects to grasp the probabilistic connections between words in a much deeper way. These QBMs might lead to more powerful, more efficient language models because they could capture really complex patterns in language data.
Okay, QNNs, QBMs. What about optimization? That seems critical for NLP, right? Training these giant models.
Absolutely crucial. And that's where another technique, quantum annealing, could be really interesting. It uses a quantum effect called tunneling to find the best solution to complex optimization problems much more efficiently than classical methods. Sort of like finding the lowest valley in a bumpy landscape by tunneling through the hills.
Huh.
The potential for NLP there is massive. Speeding up text clustering, optimizing the incredibly complex architecture of neural networks themselves, improving semantic classification, all key NLP tasks.
So beyond these specific algorithms like Grover or techniques like annealing, what about the bigger picture of quantum machine learning, QML, for NLP?
Yeah, QML is kind of the umbrella term for applying quantum principles more broadly within machine learning frameworks. We're seeing research into things like quantum support vector machines, QSVMs, quantum random forests, quantum nearest neighbor algorithms. The idea is that these quantum-enhanced algorithms might perform better on classification and regression tasks in NLP, especially when you're dealing with truly enormous, high-dimensional data sets where classical ML starts to struggle.
This all sounds amazing, but maybe a bit theoretical.
Right.
What's the reality on the ground? Are people actually doing this quantum NLP stuff now?
It's definitely early days, you're right. A lot of it is still theoretical work, small-scale pilot projects. But the big players are investing seriously. You've got IBM Quantum with their Qiskit platform exploring quantum ML. Google Quantum AI is working on algorithms for optimization and deep learning. Then there's Xanadu using photonics for quantum computing, testing QML on text. The MIT IBM Watson AI Lab is specifically looking at hybrid quantum AI models.
So industry is definitely interested.
And academia, too. Lots of research at places like MIT, University of Toronto, ETH Zurich. It's a very active emerging field.
Okay, let's get concrete. What are some specific use cases where you could really see quantum making a difference in NLP?
All right, well, one obvious one is quantum accelerated sentiment analysis, figuring out if text is positive, negative, neutral. Classical methods can be slow on huge data sets. Grover's algorithm could potentially speed up the pattern matching and clustering involved, letting you analyze sentiment across, say, social media in near real time.
Okay, faster insights from massive amounts of text. That makes sense. What else?
How about highly scalable real-time translation? Machine translation like Google Translate or DeepL is incredibly complex. Quantum approaches, maybe using things like tensor networks processed on quantum hardware, could potentially parallelize the processing of these huge language models. The dream is much faster, more accurate translation, maybe truly seamless real-time communication across languages.
That would be absolutely game-changing. And what about the AI assistants we talked to? Siri, Alexa? They still feel a bit limited sometimes.
Yeah, they definitely struggle with deeper context and ambiguity. Quantum could potentially help there too. For one thing, using quantum vector spaces might allow for richer, more nuanced representations of word meanings, so the AI could grasp semantics better. And second, quantum annealing could help optimize the complex models that drive conversations, maybe leading to assistants that can handle much more natural, complex dialogue.
So taking a step back, if these quantum advancements really pan out, what's the big picture for NLP?
I think the big picture is potentially revolutionary. We're talking exponential speedups for certain tasks, much better optimization, maybe even lower energy consumption for training these enormous models eventually. But it could also open doors to entirely new capabilities. Think about multimodal AI systems, AI that understands text, images, and sound all together. Imagine an AI interpreter that doesn't just translate your words in real time, but also accurately reads and conveys the emotion from your facial expression and tone of voice, a much deeper level of communication understanding.
Okay, that future sounds incredibly exciting. But
Right.
let's bring it back to Earth a bit. What are the big roadblocks right now? What needs to happen before any of this becomes mainstream?
Right, reality check time. We're currently in what people call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, today's quantum computers are still relatively small intermediate scale, and they're very susceptible to errors noisy.
Noisy, meaning the qubits aren't stable.
Exactly. Qubits are incredibly delicate. They lose their quantum state, decohere very quickly due to interactions with their environment. Think of it like trying to do calculations during an earthquake. This quantum noise is a massive challenge. It requires really sophisticated error correction techniques, things like surface codes, which basically use many physical qubits, just to create one stable, reliable, logical qubit you can actually compute with.
So you need way more physical qubits than the logical ones you can actually use.
Way more, yeah. So building large-scale, fault-tolerant quantum computers is a huge engineering hurdle. Plus, we still lack industry standards, mature software tools, and honestly, enough people with the expertise to bridge quantum computing and NLP effectively.
Okay, those are significant technical hurdles.
Yeah.
What about the broader impacts? If this tech matures, what are the societal concerns? Privacy, security.
Huge concerns. On the privacy front, the sheer power of quantum analysis could potentially make it easier to de-anonymize data, even data that was thought to be safe, and security. Well, we mentioned Shor's algorithm. It poses a direct existential threat to the encryption that underpins almost all secure communication and data storage today.
So we need new encryption.
Urgently.
Yeah.
The whole field is racing to develop and deploy post-quantum cryptography, new encryption methods resistant to quantum attacks. It's a massive transition that needs to happen before powerful quantum computers arrive.
And what about jobs? We hear about AI and automation already. Does quantum NLP accelerate that?
It certainly could. Areas like translation, maybe some forms of journalism, customer support. Quantum could potentially accelerate the automation trends we already see, which means we absolutely need to think about adapting our education systems. Teaching quantum computing skills, yes, but also using AI itself, maybe as advanced tutors, to help people reskill and adapt.
We've also seen problems with classical AI generating fake news. Does quantum make that worse? The potential for manipulation.
That is a very serious worry, yes. Classical models can already create pretty convincing deepfake text. Quantum optimization could potentially make these models even better at generating highly personalized, highly believable disinformation at incredible scale. Imagine targeted fake news campaigns generated instantly by quantum-assisted AI.
That sounds terrifying. How do we defend against that?
It's going to require a multi-pronged approach. Things like quantum-based authentication methods might help verify information sources. We'll need strong ethical guidelines for AI development and deployment. And definitely international cooperation and regulation.
Which leads to the whole regulatory challenge, I suppose. This technology is global.
Exactly. We need global conversations and frameworks. Who gets access to this power? How do we prevent misuse by criminals or rogue states? How do you balance encouraging innovation with ensuring safety and security? We're seeing early steps. The EU AI Act touches on high-risk AI. The US has security guidelines. China is investing heavily, but also thinking about control. But a coherent global approach is still very much needed. It's complex.
So wrapping this up, what's the takeaway here? The connection between quantum computing and NLP, it's clearly there. It's powerful. The promise is huge exponential speedups, maybe deeper understanding, more efficient models. But, and it's a big but, we have to be realistic. We're still in the early days. The tech hurdles are significant. It seems likely that hybrid approaches combining classical and quantum techniques will probably be the first practical steps we see. Ultimately, the future of quantum NLP really depends on how we navigate this, how we balance the incredible technological push with responsible ethical development and deployment. It's definitely a journey of discovery and, yeah, a challenge for all of us to think about. This deep dive into quantum-assisted NLP was really sparked by that insightful essay from Jurko Schneppat. You can find more of Jurko Schneppat's work over at schneppat.de. Thank you so much for joining us on this deep dive. Until next time.